Reductions of carbon compounds are another way to prepare alcohols. This reaction method basically involves an addition of H- hydride anion onto the carbonyl group, which then generates an alkoxide which is protonated to give us an alcohol. And so this is a reduction of a carbonyl compound through sequential addition of first hydride anion and then hydrogen plus cation, i.e. proton. The sources of hydride anion are two compounds that are very commonly used, and this is lithium aluminum hydride and closely related sodium borohydride. These compounds are known as complex hydrides because they're not sources of H- anion per se, but instead have these complex anions such as borohydride anion and aluminum hydride anion. In both of these complex hydride anions have a delta plus end on aluminum and delta minus end on hydrogen, which makes hydrogen polarized in the direction of nucleophilic species. Both of them are sources of H-, but lithium aluminum hydride is a stronger source since aluminum is less electronegative. And their mode of operation basically involves the case of sodium borohydride involves a transfer of H- onto a carbonyl compound and removal of BH3, which is then an atom protonation. This gives us our alcohol. And this is an example of a carbonyl compound reduction. Sodium borohydride is the milder of the two reagents, which means it can be used to reduce aldehydes and ketones, but not esters or acyl chloride. So this is an example of a reaction sodium borohydride where we take this phenylacetaldehyde and reacting with sodium borohydride in ethanol. And this is an important point, that this sodium borohydride works in ethanol, works in methanol, even water. We're able to get this alcohol. The fact that this works in ethanol is quite remarkable because sodium borohydride is a source of hydride, formerly a source of hydride anions, and hydride anions are very basic, but obviously not basic enough to be protonated by ethanol. So sodium borohydride is less reactive than lithium aluminum hydride, which also means that it's more selective, since it reacts with only chosen very reactive functional groups. On the other hand, lithium aluminum hydride is very reactive. It will reduce, for example, an ester all the way down to an alcohol. Okay? But if you notice, this compound has to be used in ether. And the reason for that is it's too basic. So if it's exposed to the alcohol, lithium aluminum hydride will instantly deprotonate. And will give us a range of aluminum-3 species, which, depending on the pH, can precipitate as aluminum hydroxide or not. Okay, but the point here is that while lithium aluminum hydride can be used to reduce almost any carbonyl compound down to an alcohol, it is very reactive, and therefore it's sensitive to water, sensitive to moisture, sensitive to alcohol. So it has to be operated in anhydrous solvents such as ether. On the other hand, sodium borohydride is much less reactive. It can work in water, alcohol, methanol, ethanol, but therefore it will not be able to reduce every functional group. It reduces only aldehydes and ketones. Finally, alcohols can be obtained from ketones and aldehydes by simple reduction with hydrogen. If we use just platinum, this will probably not work, but if you use the so-called Rene nickel, which is a very finely divided suspension of nickel, then we will be indeed able to add 2 hydrogens over the CO double bond and affect reduction of its compound. This is rarely used for carbonyl compounds. Lithium aluminum hydride or sodium borohydride reduction is much more useful in general, but it's sometimes used for compounds which have both a carbonyl and a double bond in there. If you want to reduce them both in one step without first using hydrogen and then using lithium aluminum hydride, then Rene nickel will work. And so running this reaction in a single step will give us a saturated alcohol at the end.